Sluices features a massive cantilever structure in which 52.2 meters of the total 86-meter cantilevered wing is open without any support below. To support this enormous cantilever spanning 11 stories with relatively short supports, sluices adopted a unique structural system rather than resisting the enormous loads simply through the bending strength of horizontal phalanges. This method allows the cantilevered section to behave as one giant H-shaped bending member, where each floor slab acts as the flange and the central double shear wall acts as the web, enabling the entire structure to function as the bending system. In this system, the structure serving as the lower flange is designed as an inclined strut, which provides significant advantages in resisting moments. While this form was also part of the architectural strategy to create an opening, it affords substantial structural benefits both at the individual floor level and in the overall system. If the struts in sluices had been merely certain walls for design purpose, each floor would have had to resist a 5.2-meter cantilever load without support underneath. In lower floors, where cumulative loads from upper levels concentrate, this would have led to intolerable structural burdens. Sluices employed a distinctive structural approach without wasting the inclined plane by utilizing the slope as an active load-bearing member. The struts are inclined at 31.61 degrees from the horizontal, transmitting loads downward at an angle as both horizontal and vertical forces. Since the struts are part of the cantilever, they inherently act as flexural members. However, due to their inclination, they do not rely solely on shear and bending resistance. They also transfer loads downward through axial forces, thereby acting as compression members as well, a hybrid structural role. The compressive forces and moments transmitted along the struts are further transferred to the massive underground shear walls and footings previously described, which ultimately convey the loads through the compression foundation system composed of steel pipe piles. This forms the load-bearing mechanism that supports sluices' cantilevered section. While the struts offer significant structural advantages, there are unique members that pose potential challenges, such as ground settlement of the support structure during construction, long-term deformation due to creep, and deflection from self-weight. Careful design and meticulous construction were essential to address these issues. Since the cantilever of sluices is located outside the L-shaped underground structure, it was constructed on a temporarily reclaimed ground between the inner cofferdam and the outer cofferdam used for underground concrete placement. As sluices created an opening by lifting a corner of the initially square-shaped site, temporary ground was constructed in the cantilever area and the central courtyard to allow the above-ground structure to be built. This reclaimed ground provided a working platform for casting and crane installation, as well as passages for equipment and vehicle access. Inside the inner cofferdam, a total of 805 precast piles and steel pipe piles were installed. Additionally, about 70 temporary steel piles were installed outside the inner cofferdam at the virtual location of the cantilever section, taking into account the upcoming construction process. While the structural piles installed inside the inner cofferdam were embedded at NAP-4 meter to connect with the B2 basement structure, the temporary piles were installed to withstand the loads during the cantilever construction, with their heads positioned at sluices ground level, NAP 2.2 meter. These temporary piles were installed at approximately 2.8 meter intervals and were later integrated with temporary structures to support the loads during the strut construction process. Afterwards, sand was reclaimed via barges, completing the temporary ground needed for construction. To stably transfer the massive scaffold loads, Supporting the cantilevered walls on the weak ground, a temporary grid of reinforced concrete beams was constructed at the base of the site. Since the formwork and scaffolding had to function as a temporary support structure until the reinforced concrete struts reached sufficient maturity and could act structurally, ensuring their structural stability and strength was essential. However, the soft ground and temporary sandfill were insufficient to bear the loads descending from the scaffolding. Therefore, temporary piles were installed. To transfer the loads from the scaffolding to these piles, a grid-shaped foundation was cast on top of the previously constructed sand-filled ground, and temporary piles consisting of tremors, longitudinal and diagonal beams arranged in alignment with the direction of the compression shear walls. These beams were arranged in a staggered L-shaped pattern at 5.2 meter intervals, corresponding to a spacing of each cantilever floor, and diagonal beams tied the entire system into a unified structural grid. This system dispersed the concentrated point loads from the scaffolding over a wide area and transmitted them to the temporary piles. The grid beams were large reinforced concrete members with cross-sectional dimensions of approximately 1000 times 500 mm cast in place on-site. The beams were laid orthogonally to form a grid mesh, and beneath the two lines of cantilever walls, this grid structure was rigidly connected to the densely spaced temporary piles head, providing stable support. The cantilever struts of sluices were constructed by dividing them into horizontal layers corresponding to each floor and casting them sequentially along these sectional zones. This method was adopted to prevent the possibility of concrete sloping downward due to its self-weight during casting on inclined struts, and to efficiently manage material layout, workflow, and safety in a challenging environment where the inclined structure had to be built without any supporting structure beneath. In line with this sector-based construction method, the strut formwork utilizes a modular kickstage scaffolding system and TOCA's Top 50 modular formwork. The TOCA Top 50 is a modular system that can form large formwork panels by combining standard components such as H20 timber beams, steel rollers, and plywood, depending on site conditions. As listed, these top 50 formwork panels were fabricated to match the shape of the inclined walls and installed on a special inclined frame called the jukan. To support the cantilever walls, large temporary scaffolding was erected. Unlike typical architectural scaffolding, this served as a shoring structure, a medium to heavy-duty load-bearing system. The quick-stage shoring system used in the sluices project was a modular scaffold where horizontal and diagonal members can be quickly connected to vertical members. Sluices employed high-strength quick-stage components using S355 grade steel for scaffolding members and thick steel pipes to enhance rigidity. As a result, even very large loads could be supported with relatively few scaffolding members, and stability was ensured so that allowable loads did not decrease even with increasing scaffold height. This supporting scaffold structure was built in a step from following the shape of the cantilever wall. Scaffold towers were erected in a grid pattern on the horizontal plane, and as they rose upward, some sections were set back step by step to match the slope of the cantilever walls. Since all scaffold members were connected in a regular modular system, a consistent pattern and spacing were maintained throughout the large structure, making it possible to relocate and elevate previously used modules for reuse. Braces were installed throughout the structure to resist lateral forces from wind or the self-weight of the struts, and at the base, Additional steel reinforcements and connections were applied to prevent buckling. Additionally, during casting, the formwork support frame was anchored to the previously cast inclined wall, which enabled the horizontal loads generated during concrete pouring to be transferred to the existing concrete wall rather than the scaffolding. As a result, only vertical loads acted on the scaffolding itself, allowing for stable load support without bending moments or additional settlement. Beneath this scaffolding system, as previously mentioned, temporary reinforced concrete grid beams were installed on top of the sand reclaimed ground to widely distribute the loads. By thoroughly reinforcing the entire load path from the foundation to the upper formwork, the structural stability of the scaffolding system supporting the massive cantilever was ensured. To construct the inclined wall, which was divided and built one story at a time, large formwork panels were first installed at the required angle of inclination. These formwork panels were supported by a special inclined frame called a chicane, placed on top of the scaffold structure below. Once the formwork panels were accurately fixed in position and angle, and the wall reinforcement was completed, concrete was poured. Due to the nature of the inclined structure, the concrete was cast in multiple stages to form horizontal layers. The casting process was divided into the slab joint areas and midwall segments so that each pour would form a horizontal surface. The internal space of the formwork was sectioned accordingly, allowing the concrete to be poured sequentially in a controlled manner. This method prevented the concrete from flowing down the slope and ensured stable placement. Furthermore, the construction joints were kept in a moist state to allow for monolithic bonding between pours. Once the lower portion of the wall gained sufficient strength, the formwork was removed. This was done by loosening the threaded jack spindles of the juke support frame to create a gap between the panel and the concrete surface. Then, the entire formwork panel was lifted using a winch or similar hoisting device and reused for the next section of the wall. After lifting the formwork to the height of the next story, the support frame was reassembled on the scaffolding and the formwork was installed once again. At this stage, the support frame for the next sector was anchored to the already cast inclined wall below. This anchoring ensured that the lower inclined wall would resist the horizontal forces generated during the upper level concrete pouring. After adjusting the position and angle of the formwork with precision and complementing the reinforcement, the concrete was cast for the next story. This process was repeated step by step for each subsequent layer of the inclined cantilever wall. To accommodate the construction process, the inclined wall was divided and built in sectoral units corresponding to one story each. However, this division led to construction joints at its interface, which could potentially pose structural problems. Given the enormous axial forces and moments borne by the struts, it was essential for the structure to behave as monolithically as possible. Therefore, the contractor meticulously planned the process so that the next section of the inclined wall would be cast while the lower section had gained partial strength but remained in a moist state. This approach maximized continuity and ensured the best possible level of monolithic behavior between sections. In addition, supplementary reinforcement was provided to strengthen the potentially weak construction joints. Because the struts are inclined at 31.61 degrees from the horizontal, the loads transmitted along the axis of the strut include a horizontal component greater than the vertical one. This horizontal force could cause shear failure at the relatively weak construction joints, especially those cast in horizontal layers such as slab interfaces. While the main longitudinal reinforcement in the strut resisted some of the shear, and the joint surface were intentionally roughened to increase frictional resistance, these measures alone were not sufficient. Therefore, shear reinforcement was added. For ease of construction, the shear reinforcement was arranged vertically. It was bent into a jet shape, wrapping around the bottom horizontal reinforcement, and then extending upward to wrap around the upper horizontal reinforcement. In this way, the shear bars penetrated the joint vertically and resisted shear failure caused by horizontal forces. Emerging diagonally at a 31.61-degree angle of approximately the mid-height of the underground compression shear wall, the cantilever struts, previously described, act as a hybrid structural element, functioning both as bending and compression members. Due to this dual wall, a large amount of both vertical and horizontal reinforcement was installed. The vertical reinforcement consisted of D32 to D40 rebars, and the horizontal reinforcement used D22 to D25 rebars. Within the 400mm thick struts, the thick vertical rebars were positioned toward the outer faces, while the horizontal rebars were arranged internally. These horizontal rebars were grouped into bundles with ties to produce a confinance effect, helping to prevent strength degradation within the strut due to deformation, thus improving the structural integrity of the elements. Next week, we will cover the construction process of the other areas, excluding the cantilevered strut walls. The following week, we will focus on the construction methods used to control the settlement and deflection of the cantilever structure on the soft ground at solid Swiss.